Let us see a simple and interesting application of NOT gate. Okay, so you know that in a NOT gate, when the input is logic 0, it produces output 1. When the input is 1, it produces output 0. So let me connect the output of a NOT gate to its own inputs. So this is the NOT gate. Its output I am connecting to its own inputs. Okay. And let's say the delay of this, I am assuming this is 1 nanosecond. The delay of this gate is 1 nanosecond. So in any digital device or digital circuit, so the state of a point is always, it could be either 0 or 1. So that means if I am saying that this is what is my output y is, so this y could be either 0 or 1. You can assume anything. Let us say when the power supply is turned on, so y equals to 0. So when the power supply turned on, y equal to 0. Even you can take 1, no problem. But it can't be any third state. In a digital circuit, always the output will be 0 or 1. So by default, we take it is 0, but nothing wrong if you take 1 also. Okay, so y is equal to 0. So now this 0 will be processed as input to this one. So there is no delay on the, in this connecting leads. If I am saying that this is 0, it means that here also it is 0. So if 0 is the input given to this NOT gate, so after 1 nanosecond of delay, you are going to get this is 1. So this 0 will be replaced by 1. So now the input which are earlier 0, so now when this you got 1, immediately this 0 will be changed to 1. Now when the input is 1 to this NOT gate, so its output will be 0. The moment when it is 0, now this is 0. So now this 0 will be processed again after 1 nanosecond, this will be 1. So now the moment when it is 1, this 0 will be changed, this will be 1. Now this 1 will be processed after 1 nanosecond, this will be 0. Then again this 1 will be replaced by 0, and then this 0 will be replaced by 1, and this pattern will continue. So actually students, it makes sense that if I am saying, let's say this point is A, it's natural that the output of the NOT gate will be A complements. If I am saying the input is A, now this equals to A bar. But you see that this point and this point are same. There is no element, there is no other element in between. So this point and this point is same. So this point is A and this point is A bar. So forcefully what I am trying to tell you is, I am trying to tell you that A equals to A bar. So whenever you are saying that a variable is equal to its complement, which is a contradicting things, that's why you are getting some kind of unstable behavior here. I mean, the output is not getting settled either at 0 or 1, it is fluctuating 0, 1, 0, 1, 0, 1 kind of pattern. And why it is fluctuating? Because of the delay of this. Because you have A equals to A bar you are saying, and intentionally you have introduced a delay elements. So if you observe this is 0, then after 1 nanosecond you are getting 1. Then after 1 second you get 0. Then further after 1 nanosecond you get 1, and this pattern continues. So if I ask you to draw the waveform of this, how does the waveform will look like? So I can tell that, so this was 0 at 0 nanosecond, you got this 1 at 1 nanosecond. Then after 1 nanosecond you got 0. So at 2 nanosecond it is 0, at 3 nanosecond it is 1, at 4 nanosecond this is 0, at 5 nanosecond this is 1, and so on and so forth. So if I ask you to draw the waveform, so initially at t equal to 0 it is 0, then at 1 nanosecond this is 1. So this is 1 nanosecond, so at 1 nanosecond this is continuing 1. Then at 2 nanosecond it is changing to 0, then at 2 nanosecond this is changing to 0. So this 0 is continuing, then at 3 nanosecond it is again 1. So this is 3 nanosecond, this is 1. Then this one is continuing, at 4 nanosecond it will be 0, 0. Then it will continue at 5 nanosecond, it will be again 1, and then at 6 nanosecond it will be again 0, and so on and so forth. So this pattern is being followed. So this is t equal to 0, this is t equals to 1, this is t equals to 2, 3, 4, 5, 6, 7, and 8. Now if I ask you, so what happened then? So in this case, if I am plotting the waveform is a square waveform. And if I ask you what is the time period of this waveform, the time period of this waveform is 2 nanosecond. This is 2 nanosecond. You can take any interval actually. So you can take here to here, any interval you can take. It's a periodic waveform, so it doesn't matter what is my point of observation. So it is 2 nanosecond. So we understood if I'm taking a simple NOT gate and if I am connecting its own output to its inputs, so it is producing unstable behavior, and in every 1 nanosecond. So why 1 nanosecond is coming? Because the delay of this intentionally I have taken 1 nanosecond. In every 1 nanosecond, there is fluctuation of 0 1 0 1. So whenever there is fluctuation of 0 1 0 1 0 1, if you plot that waveform, it looks like a square waveform. So what is the time period of this waveform? Time period of this waveform is 2 nanosecond. So time period is 2 nanosecond. If somebody asks you what is the frequency, frequency is reciprocal of time period. So it is 1 by 2 into 10 power 9, this much of hertz. So this is what the answer is. All right. So this is what we understood for a particular NOT gate, a single NOT gate I have taken. So let us extend this idea to more number of NOT gates. Now imagine a case, instead of taking one NOT gate, I have taken two NOT gates. So I have taken two NOT gates, and output of this NOT gate I have connected to input of this. Now in this case, what is the thing going to happen? So again, as usual, so you can say this is your output Y is. So initially you assume that this is 0. So initially you assume that this is 0. When the power is switched on, this is 0. Now the moment when this is 0, indirectly I am saying that this is also 0, because this is the same line. So if you say this is 0, so this 0 will be coming here. So this is again 0. So this is 0 means its output will be, so again you take any, like let's say you take this is 1 nanosecond, the delay, or you take it 2 nanosecond, you take this is 3 nanosecond, or anything you want, you can take it, no problem. So if this is 0, then after 2 nanosecond, this will be 1. Then you got this one at 2 nanosecond, then the input to this NOT gate is 1, its own delay is 3 nanosecond. So after 3 nanosecond of this one, so this will be 0, because if the input is 1 to NOT gate, its output will be 0. So you see that earlier the input was, earlier when I have started these circuits, when I switched on this is 0. So when this 0 is propagating through this loop, once again I am getting it is 0. And it is expected. Why it is expected? Suppose if I am saying that this point is my A, now this point is your A bar. If A bar is the input to this NOT gate, so its output will be again A. So this point is A and this point is A. So A equals to A is a perfect thing, no problem. But here it was A equals to A bar. So that's why you are getting the fluctuation, but in this case you are not going to get any kind of fluctuation. Now here I have taken the initial condition as 0, students, so that's why this is happening. But let's say I have taken the initial condition as 1, then in that case what is going to happen? If the initial condition is 1, then what is going to happen? If the initial condition is 1, then this is also 1. So this is 1 means after 2 nanosecond, so this will be 0. After 3 nanosecond from this point, this will be again 1. So if the initial condition is 1, 1 second it is 1. So here you are not going to get any kind of fluctuations. All right. So for one NOT gate we have seen, for two NOT gate we have seen. Now let us go for the 3 NOT gate case. If I am taking 3 NOT gate and I am forming a loop, then in this case you should be able to tell the answer now what is going to happen. So you assume that this delay is 3 nanosecond, this delay is let's say 5 nanosecond, and this delay is let's say 7 nanosecond. So naturally, students, you should be able to tell the answer whether it will be stable behavior or unstable behavior. So if you assume that this is your A, then this is your A bar, then this is your A, and this is your A bar. Now this point is A bar and this point is A. Now you are connecting the point A bar to A. So if you are connecting the point A bar to A, so forcefully you want to say that A equals to A bar. So naturally in this case, you are going to get the fluctuation of 0 1 0 1. So whenever you get a variable equals to its complement, the output will be always in the unstable state. It won't be either 0 or 1 the way it is happening in case of 2 NOT gate case. So it will be always 0 1 0 1 fluctuations. So for case study, let us see what it will be. So initially, let me assume that this condition is 0. If this is 0 means this is also 0, because this is the same line, right? This is also 0. If this is 0, then after 3 nanosecond, so this will be 1. So if this is 0, after 3 nanosecond, this will be 1. So 1 is the input to this NOT gate, so its delay is 5 nanosecond. So after 5 nanosecond, so 1 is the input, so its output will be 0. Then 0 is the input to this NOT gate, then after 7 nanosecond, now this will be 1. So you see that earlier you have taken it is 0. So now when the signal is propagating through all these three NOT gate, you are getting it is 1. But after how much time we are getting this? After the delay of these all NOT gates. What is the delay? Here it is 3, here it is 5, here it is 7. So 3 plus 5 plus 7, after 15 nanoseconds this will be 1. So now the moment when it is 1, so which was earlier 0, so now this will be changed to 1. So 1 will be processed, this will be 0. So 0 will be processed, this will be 1. 1 will be processed, this will be 0. So when? When after 15 nanosecond. So if I'm asking you to draw the waveform of this point, let's say, which is y. So y is 0 initially. So this 0 will be continued like this. Up to how much time? Up to the delay of these three gates. The delay of these three gates is 15 nanosecond. So initially it is 0 for 15 nanosecond. This will be continuing to 0. At 15 nanosecond, this will change from 0 to 1. So this will change from 0 to 1. And again, it will be from 1 to 0 and 0 to 1 and like this. So this is again a square waveform. So what is this gap? This gap is, if it is 0, after how much time it is 1? It is 1 after the delay of this, so 15. Then when it is again 0, again after 15 nanosecond. So this gap is 15 and this gap is 15 and so on and so forth. So the time period of this is 30 nanosecond. But imagine a case, students. So here I have taken the non-uniform delay. But if you assume the delay are identical, then what is going to happen? So if you assume that the delay is, let's say, TPD and TPD and TPD, then what is going to happen? So this gap is 3 TPD and this gap is 3 TPD. So this is also 3 TPD. So the time period here will be 6 TPD. 6 TPD. But if you go with n number of NOT gates, then this will be n TPD, this will be n TPD. So the time period will be n plus n 2n TPD. So if it is 2n TPD is the time period, then frequency will be 1 by 2n into TPD. Provided the n value is odd. So n value is odd. So you see that for the three cases, I am getting this one. But what do you think if I am taking one more NOT gate here? So here you see A bar, again it will be A. So A and A will be again matching. So there won't be any kind of fluctuation. It will be again something like this. You go with 5 NOT gate, again you will have the problem. You will have again the problem in the sense you have again the unstable behavior. You go with 6, it will be again stable behavior. So whenever you are connecting even number of NOT gates in a loop, so the output is a stable state, it will be either 0 or 1. But whenever odd number of inverters are connected in a loop, the output will be always unstable. It could be 0 or 1, 0 or 1, 0 or 1. It will be kind of fluctuation state. If you assume the delay of each gate are identical, then the time period is 2n TPD and the frequency will be 1 by 2n TPD. So this is one of the point I have written here. Whenever odd number of inverters forms a loop, it acts as a square wave generator. If delay of all inverters are same, the frequency of square wave at any point in the circuit will be 1 by 2n TPD. So we understood this conclusion. Here, friends, one more simple trick actually. Just a case study. Sometimes students get confused. So if you see this waveform which I have shown here, so this waveform is this point waveform, right? So I have drawn this waveform Y. So we understood that this is 30 nanosecond. That is absolutely fine. But somebody asked me, what is this waveform? So what is this waveform? So let's say this waveform is Y1 and this waveform is Y2. So what about the waveform Y1 and Y2? Whether their period and frequency will be same or it will be different. What is your answer? So if I ask you for Y1 and Y2, what is your answer? So see, for example, my observation is at Y1. So initially Y1 is 0. Then after how much time this is becoming 1? So Y1 is 0. Then we know that this is 1. But after how much time? So this 0 is passing through this gate and then it will be passed through this gate and this gate, then it will be 1. So ultimately, a 0 is getting changed to 1 when the signal is passing through again all the three gates. Like first this gate, then this gate and then this gate. So again the gap is 7 plus 3 plus 5, which is again 15. So here also the fluctuation is happening on every 15 nanosecond interval. So if I ask you the time period and the frequency, it will be again same. What about this point? Again, same story. If it is 1, after how much time it is 0? So this 1 is processed by this gate, and this gate. So it is 0 then. So again the delay of this and this. So 5 plus 7 plus 3, 15 nanosecond. So it doesn't matter. So whether I take the output from the last point or any point in the circuits, first point, last point, middle point, any points, any kernel points, anywhere. So output frequency or the period will be always same. Don't be under the impression like if I'm taking here, it will be something else, it will be taking here something else, it will be taking here something else. No. But if the question is whether the waveform of this point and this point and this point will be exactly same, no, waveforms won't be exactly same because this is a NOT gate. So if this is what is your output, so your input will be complement of this. So if let's say if I'm saying that output of this point is this one, if somebody asks me what is the input will be reverse one. So here it is 0, so here it will be 1 and then 0, then 1, then 0 like this. It will be complement to each other, but the period will be same. I'm not saying the waveform will be same, but the period and frequency will be same. So this is what the thing is. Let me give you a common sense based questions and let me see how many of you are able to answer this. You try yourself, friends. So suppose, for example, this kind of question is asked in one of the instrumentation paper. Otherwise, let us see that question itself. So no need to have my own this thing. So let us say this is what is the instrumentation question bank. Okay, we have the question bank chapter wise. Yeah, this question I wanted to discuss, which is a 2006 model questions asked in the instrumentation branch for 2 marks. Okay, so this is the question. Okay, one more thing. So this circuit is known as popularly square wave generator. The other name of square wave generator is astable multivibrator. So multivibrator are of 3 types: bistable, monostable, astable. So this is called a bistable multivibrator. That means whenever we have even number of NOT gates in a loop, like 2, 4, 6 like this, we say it is bistable multivibrator because the output having 2 stable states, it will be either 0 or 1. And why we are calling it is astable multivibrator? The name astable is given based on there is no stable state. So in analog circuits, these days it is not in the course, but if you see the old pattern syllabus or in your BTech you have studied this, you might be knowing this. In a astable multivibrator, there is no stable state. So the output always fluctuates. So we call this is astable multivibrator. And one more is monostable multivibrator is there. So that is different thing. But here it is astable multivibrator. Sometimes it is also known as clock wave generator or clock pulse generator, because the clock pulse what are being used in case of the sequential circuits, so they are the square waveform. So that's why, because the square waveform sometimes they call it is clock wave generator. The meaning is same. So student, here the question is, all the logic gates in circuit shown below have finite propagation delay. The circuit can be used as a clock generator if x equals to 0, x equals to 1, here x equals to 0 or 1, okay, and here x equals to y. Under what case this will work like a clock generator, that means square wave generator. So what is the answer, student? What do you think? So we know that it will work like a square wave generator if we have odd number of inverters in the loop. So how many inverters I have here? I have 1 inverter, I have 2 inverter. So you want this should also work like inverter. We have seen the property of XOR gate that 1 XOR with X is equals to X bar, 0 XOR with X is equals to X. So inverter application of XOR gate. So when a XOR gate works like a inverter, if one of the input is connected to logic 1, because if one of the input connected to logic 1, then 1 XOR X will be X bar. So naturally, if you want to make this as a NOT gate, so you have to make X equals to 1. If you make X equals to 1, then it is also equivalent to a NOT gate. So there will be 3 NOT gate and it will work like a square wave generator. But what would have been the case if it would have been a XNOR gate? If it is XNOR gate, we know that a XNOR with 0 is a bar. So in that case, instead of X equals to 1, we would have connected to 0, so that it will work like a NOT gate. Okay. And in gate exam, students, multiple time questions are being asked. If you want to see, I can show you. So in the logic gate topic, you see this is one questions. A ring oscillator consisting of 5 inverter is running at a frequency of 1 megahertz. The propagation delay per gate is how much nanoseconds? So that circuit is a ring oscillator, right? So because the NOT gates are in the ring, so in that sense it is also known as ring oscillator. That to be 5 inverter, odd number inverters. So it is running at a frequency of 1 megahertz. So we know that in the square wave generator or a ring oscillator, the frequency is f is equals to 1 by 2n TPD. So n value is 5 and frequency is given 1 megahertz. So you need to find the TPD. You can substitute these all value and you can solve for TPD. And you see, this is another question. The same ring oscillator, the propagation delay of each inverter is 100 picosecond. Okay. So then the question is, what is the fundamental frequency of outputs? So frequency they're asking, answer is 1 by 2n TPD. So 1 by 2n TPD. So here n value is 5 and TPD value is how much? 100 picosecond. So 100 into 10 power minus 12. You can substitute here and you can simplify. Okay, so this is what is this applications that not get as a square root generator. I hope this logic is clear to all of you students.